Let's finish up our description of the respiratory system by zooming in to the smallest level that we're going to work at here. We're going to look at hemoglobin and remind ourselves of the partial pressure gradients that happen between the atmosphere and the blood if we're looking at external respiration, or between the blood and cells of the body through capillaries when we're looking at at internal respiration. We're going to also talk a little bit about how oxygen and carbon dioxide travel through the blood, and then finally wrap up with how ventilation is controlled, depending on conditions in the body. We're going to go over these SLOs in this video. These are all basically in order. This will kind of conclude all of the SLOs for the chapter. The only ones I probably didn't talk about altogether were the ones that are related to like COPD and other kind of disorders, but those are not hard to put together once you've had a chance to read them in the text, I think. This Focus 22 figure is pretty helpful for trying to understand how hemoglobin saturation works. It's kind of a multi-part figure, so I'm going to kind of work through it panel by panel. So here, this shows you this basic kind of sigmoidal curve that the hemoglobin saturation graph follows. If you look at the axes, notice the x-axis, that's the partial pressure of oxygen in millimeters of mercury going from zero, basically fully, basically zero oxygen, to 100 millimeters of mercury, which is approximately what the partial pressure is of oxygen. And the y-axis shows how loaded the hemoglobin is, going from fully saturated up at the top to completely unsaturated, so bound to zero oxygens. We remember that when hemoglobin is fully saturated, each hemoglobin molecule can carry 4 molecules of oxygen. So let's compare the difference between what's happening up in the lungs to what's happening out in the tissues. Now, remember from before, when the blood gets to the lungs, it's mixing with alveolar air, where you have a PO2 of about 104 millimeters of mercury. So the pulmonary veins that leave the alveoli are going to be basically fully loaded, be fully saturated. If we look to see how this looks on the graph here, so in the lungs, dude at the beach, he's up at that very top of the graph because at sea level there's a lot of oxygen, so it's easy for hemoglobin to become fully saturated in the amount of time it has to pass through the pulmonary capillaries. On the other hand, the lady who's up skiing, now when you're at high altitude, which I think we talked about before when we were doing anemia. When you're at high altitude, there's less oxygen in the atmosphere, so the partial pressure is lower, so the average saturation of hemoglobin is also a little bit lower. I mean, only slightly lower than 100%, but it's pretty close to saturated, whether you're at most kinds of altitudes that humans live at. Things are different, though, if we consider what the saturation of hemoglobin is when we're looking at in working tissues. Now remember, the blood leaving the lungs and entering the tissue capillaries has that fully loaded, fully saturated 100 millimeters of mercury, but the tissues, they'll often have 40 millimeters of mercury or less when you get out there in the periphery, depending on how active they are. So we know from before this means that oxygen is going to roll down its partial pressure gradient, so it's going to dissociate from the hemoglobin to go to the tissues where it needs to get used. So let's see what that looks like on the saturation graph. So if we compare, girl out on the common where you have these resting tissues, in most resting tissues, a decent average PO2 that we'd see in those tissues is around 40 millimeters of mercury. So if you kind of trace up on the graph from 40 millimeters of mercury on the x-axis up to where it intersects with that sigmoid curve, and then trace over to the y-axis, that tells you that hemoglobin is about 75% saturated. So about a quarter of the oxygen that's carried in the blood is going to get unloaded at those resting tissues. So for your average molecule of hemoglobin, it's going to leave that capillary still with like 3 molecules of oxygen on it. because the demand for the oxygen isn't that great. Now, that blood that's leaving that tissue capillary, it's going to go back into venules and then eventually to one of the vena cavae and then back to the right side of the heart. So I think we have the impression that blood is like either oxygenated or deoxygenated, and that's really not true. Oxygen in the blood, it really can vary depending on what's happening in the rest of the body. So in the case of Girl on the Common, what's happening there is, the blood that's returning to the heart from the periphery is still pretty saturated. So it's not like, all the oxygen gets dumped all at once. But it can be different if we're looking in, so for Michael Phelps, whoever this is, swimming down below. Where here in active tissues, it's not uncommon for the PO2 to be lower than, around 20 millimeters of mercury, or could be even lower, depending on how actively metabolizing those cells are. Now, this is like showing what? Like the biceps brachii, but this is going to be true for any actively metabolizing tissue, whether it's nervous tissue or smooth muscle in the gut or secretory cells. Any cells that are using energy to do their thing are going to need oxygen in order to make that ATP, right? So even though the muscle is what's being shown here, it's going to be true for whatever kind of tissue we're talking about. So anyway, if you were looking at tissue and actively metabolizing tissues, so here they're estimating around 20 millimeters of mercury, you follow that up to the line, and you see in that case that the hemoglobin's only like 40% saturated. Now, in case you're wondering, like, is that all there is for trying to interpret that graph? I mean, like, it really is. The numbers that are usually important for people to remember for me are like, what's the PO2 in the lungs? What's the PO2 in the tissue beds of like resting tissues, and what's the PO2 of tissues when they're actively metabolizing? So that like 100, 40, and 20 are the numbers that I tend to kind of work with. But of course, in real life, they can fall anywhere along the line here. Now, I mean, you can imagine if you held your breath, if you're just sitting in your chair and decide you're going to hold your breath, it's going to take a few passes for the blood to be moving through the body before it becomes fully fully unsaturated. So your blood doesn't really become deoxygenated unless you stubbornly hold your breath. And then even then, there comes a point where you get lightheaded and you pass out. And then when you pass out, you start breathing again. So passing out is one way for the body to kind of help you, make you horizontal, so that, and also to kind of prevent you from doing something stupid like trying to, hold your breath to death or something. Anyway, this basic curve is typical for how saturation works, how oxygen saturation works for hemoglobin. But there are different conditions in the body that can change exactly what the shape of that curve is. Here we're looking at the effect of temperature compared to how that changes the shape of the dissociation curve. So your typical body temperature is around 38 degrees C, like on average. So that's the curve we were supposedly looking at before. Now, notice as you heat up, as your muscles are more active, as other cells are more active, what do? They produce a lot of waste heat. That waste heat can raise your core temperature. Now, we have ways to try to cool down our core temperature, of course, like we'll try to get more blood up to the skin surface, try to sweat, try to do some evaporative cooling that way. But there comes a point, and we'll talk about this when we're doing metabolism later, there comes a point when it becomes too difficult for the body to shed heat. When that's the case, hemoglobin can denature a little bit. So the effect of denaturation makes it easier for it to dump off, for it to be able to dump off oxygen into the tissues. So, for example, if we were looking at 40 millimeters of mercury of PO2 at 38 degrees C, if we follow that up, that puts you at about, 70% saturation if you look at the graph. So 40% 40 PO2. If we follow up to the purple line, the 38C line, that gets you to around 70%. But when your body temperature is 43 degrees C, we go from the 40 on the x-axis up to that fuchsia line, the 43 degree C line, and there it's like 50% saturated. So the difference in highly metabolically active and a highly medically active body, a body that's heated up, it's easier for hemoglobin to shed those molecules of oxygen because of the denaturation, because the body's gotten too warm. So basically, so the effect of this in active tissues, if your either your local tissues or your core temperature is heated up past the 38 degrees C, it makes it easier to dump off that oxygen, which is ostensibly what you want, right? These are metabolically active cells. You want to dump out a lot of oxygen on them so that they can make the ATP that they need. But let's look at it the other way. I'm always reminded, I always think of when you hear stories in the wintertime of like people falling through the ice and they stay under the ice for like half an hour or 20 minutes or something, and but they still survive it. One of the reasons why that happens is because there's like this shift leftward in that sigmoidal curve. So again, at 40 millimeters of mercury, if your body temperature is only at 20 degrees C because you're really, really cold, notice there your hemoglobin's still like 90% saturated. So part of the reason why people can survive being underwater in cold water for like a long period of time is because of this relationship where even though you're not ventilating, the amount of oxygen that's in the blood will still stick around and go to the places where it's going to be really needed the most, mostly in this case probably to nervous tissues in order to keep people so they can survive this. So in this case, if we're comparing it from the 38 degrees C line, as temperature goes up, we get what we call the right shift in the saturation curve. But when we get colder than 38 C, then we have the so-called left shift. Right shift makes it easier to dump off oxygen. Okay, now let's compare that with if we're looking at carbon dioxide. Now, your normal PCO2 is around 40 millimeters of mercury, so we can talk oftentimes about PCO2 and the pH of the blood as being more or less interchangeable for reasons I'll explain a little bit. But your blood is slightly on the basic side. On the other hand, if you are actively exercising, there's going to be more carbon dioxide that gets dumped into capillaries because that's one of the waste products of metabolism, right? So that's going to make the blood more acidic. Not like acidic down to 4 or 2 or something, but still more acidic than the 7.4 that it's supposed to be at. So again, we see this like rightward shift, and the same thing happens. With increased blood acidity, it has the effect of making it easier for oxygen to get unloaded into working tissues. On the other hand, when the opposites happen, if you're hyperventilating and your PCO2 ends up getting a lot lower than usual and makes the blood more basic, then in that case, the blood is going to tend to hold on to that oxygen a little bit more easily. So, but again, what we're seeing in both of these graphs, what we're seeing is in the effects of exercise, either if you look at it in terms of temperature or if we look at it in terms of acid produced that gets dumped into the blood, we see this rightward shift so that it's easier for hemoglobin to become unsaturated. Okay, now to this gets a little bit hairy as well, and I'm going to zoom in on these figures. But the first thing I want to focus on is the notes that I wrote on the side here, which is to say that when we look at how these different gases travel in the blood, there are a few different ways that they can go. In the case of oxygen, it's really got one main route, where most of the time oxygen is traveling with hemoglobin, so what we call oxyhemoglobin, this HbO2. But it's also possible for oxygen to travel in the blood as a gas, but that really doesn't happen that much, because remember, it's like only a 20th as soluble as carbon dioxide is. So that's relatively, most of the oxygen is not traveling that way. Most of the oxygen is going to be traveling in association with hemoglobin. Carbon dioxide, on the other hand, has a few different choices. It can travel associated with actually the globin chains, in association with the globin chains of hemoglobin. So traveling is what we call carbaminohemoglobin. It can also travel as carbonic acid, either made in the plasma spontaneously or made with the assistance of an enzyme in red blood cells, or it can travel as a gas in solution as carbon dioxide gas. Again, because it's a lot more soluble than oxygen is. So let's zoom in on first looking at internal respiration. So here, if we're looking at gas exchange between the cells and the between the red cells and the cells of the tissues. Oxygen first. So, and the way that you read this cartoon is the width of the arrows shows you like how fast or how much a given gas is traveling in that route. So if you look at oxygen first, first of all, we see this, oxyhemoglobin will dissociate into oxygen plus hemoglobin, so it's a naked hemoglobin. And so most of that oxygen can leave really quickly out that route, and then it just slows down a little bit once it gets into the interstitial fluids, just because it doesn't have a carrier molecule there and gets to the working cells. Similarly, there's a little bit of oxygen that's in the plasma dissolved anyway, and that's also going to that can move straight across as well. But all the blue arrows, the carbon dioxide, that's all moving in the other direction. So going through in kind of the same order, carbon dioxide can bind with the hemoglobin to become that carbaminohemoglobin. That's one way it can go. But then there are two ways for carbon dioxide to travel as an acid. I'm going to do first the spontaneous way, what's labeled as the slow way. So carbon dioxide leaves the interstitial fluid, goes into the plasma, it bumps into bumps into water, and then it turns into a weak acid called carbonic acid. That's at H2CO3. Carbonic acid then dissociates, so there's the carbonate part on one side, and then the hydrogen ion, which is going to bind up to other plasma proteins. So we call that the slow way because it happens spontaneously without the assistance of enzymes. On the other hand, within the red cells, there's an enzyme there called carbonic anhydrase. And so in this case, carbon dioxide goes into the red cell, and then it's combined with water with carbonic anhydrase, again to make carbonic acid. And then here what happens is there's what's the so-called chloride shift, where the carbonate leaves the red cell and goes out into the plasma, and chlorine is brought in to kind of keep it sort of neutral there. And then that hydrogen ion will then bind with the hemoglobin instead of making the red cell more acidic. So and the other way is it can just go out as a gas. So basically, when we're looking at this, it's the only one that I think is tricky is the carbonic anhydrase versus spontaneous formation of carbonic acid. But that's that's what we have for if we're doing internal respiration. For external respiration, so if we're moving gases from the between the alveolus of the lung and the blood, all those arrows are going in the opposite directions. So again, we look at oxygen. Oxygen mostly is going to be connecting with with hemoglobin, and in this case, the oxygen is going to take the place of the hydrogen ion that had come in from the carbonic anhydrase before. A little bit of oxygen also comes in dissolved in the plasma. For the carbon dioxide, again, there's the part that's dissolved in the plasma, so that's easy. There's the spontaneous way because of the partial pressure of carbon dioxide wants to leave the blood, so it'll end up like reforming that carbonic acid, which then splits into carbon dioxide and water. So notice this is now a reversible reaction. It's like all these arrows are moving the opposite direction. Similarly, the chloride shift works the other way through that antiport system, where the chlorine is lost, the carbonate group gets brought back in, reforms carbonic acid, which then carbonic anhydrase splits into carbon dioxide and water, and then it dumps out the carbon dioxide that way. And the last one is the hemoglobin way, where carbon dioxide just loses its attachment from carbaminohemoglobin and ends up leaving. So I would take a little bit of time going back and forth between these two, but the main thing comes back to like what these notes are on the side. So just so you understand, there's the hemoglobin way, there's the dissolved in a gas way for both of them, and then carbon dioxide only can travel as carbonic acid, but it's got two different ways that it makes that happen. Okay, so to kind of finish up, let's talk about how ventilation is controlled. Now, we know that ventilation is like kind of automatic, but it's not autonomic. The diaphragm, the intercostal muscles, those are skeletal muscles. Skeletal muscles are controlled by somatic nerves, not by autonomic nerves. Now, there are these centers in the pons as well as in the medulla that are going to be responsible for kind of setting up your baseline rhythm of ventilation, but also modifying that depending on information about the chemistry of the blood that comes in from the periphery. Okay, so I guess the basic thing to remember is these deep brain centers are interacting with one another that are setting up the basic rhythm for respiration. And that basic rhythm is to kind of keep the blood as oxygenated as it needs to be for whatever your baseline level of activity is. So this works when you're running, this works when you're sitting in class, this works when you're sleeping. There's a condition called sudden infant death syndrome, SIDS. They used to call it crib death back in the old days, where little kids, infants will kind of, especially infants that go to sleep on their bellies, sometimes their breathing rate gets slowed down to a point where they are unable to get enough oxygen in, especially if their mouths are like flat down on the mattress or whatever they're sleeping on. So part of the reason why we put babies to bed on their backs now is because, to try to avoid this. Usually what happens, because like little babies, they don't roll around. They little babies are great because like they stay right where you put them. But when you put a baby to sleep on its back, it's usually not gonna succumb to that because if they're breathing into the open air. But if they roll and they kind of find themselves in a corner, or if they're on their bellies, then sometimes they can get their mouths blocked, so it makes it more and more difficult for them to breathe. And a similar thing actually happens with people who have sleep apnea. Now, many people snore when they sleep, but for people who have real sleep apnea, what happens is there'll be this slowly decreasing amount of ventilation, and then a person will stop breathing for a while, and then there's like a big snore that happens when the medulla finally goes, okay, time to breathe. So that's what is responsible for people who sleep with sleep apnea. That's the problem with the really raucous snoring that they have, is because it's sort of the amount of breathing sort of slows down gradually, but then has to, because of blockages in the pharynx. So that has to that basically gets resolved the same way. Now, how is it that, and this is like a super uninformative figure in some ways, basically what are the places where the controls actually happen to set up your respiratory rhythm? There are, I'm just going to start at the top here. So the cerebral cortex, like the motor parts of the cortex, are responsible for your voluntary control over your breathing. So when we were in class together and I'd have you breathe in and out, you were controlling that rhythm of your breath there. Or if you're playing a wind instrument, or if you're singing or something, we're still regulating what your basic ventilation pattern is. So you can either speed it up or slow it down. That's what that plus or minus means. If you go along let's go down the left side first. So this says your other receptors, emotional stimuli. So if you are anxious, if you are afraid, if you are in pain, that can make your ventilation rate go up. Or in the absence of those conditions, can make ventilation rate slow down. So we think of people hyperventilating when they're freaking out, and that's what's kind of happening. They're kind of regulated through the hypothalamus. There are peripheral chemoreceptors as well that are located in the aortic arch and also in the carotid sinus. Now, what's interesting about those is those are actually, remember, that's the same place where the baroreceptors were for blood pressure, also up there in the aorta, in the carotid sinus. Yes, it's sensitive to low oxygen. That'll make ventilation rate speed up, or high CO2 or high acid. But really, it's carbon dioxide. That's the one that has the biggest push for setting your ventilation rate. So when you have high amounts of CO2 or high amounts of acid in the blood, that's going to increase your ventilation rate so that you can try to blow off that extra CO2 and bring in more oxygen to replace it. The central chemoreceptors, that's the brain being sensitive to hypoxia. So If the brain needs more oxygen to be coming on board, that's also going to be increasing the the rate of breathing as well. So the difference between central and peripheral chemoreceptors is basically where they're located, either out there in the periphery or there with the brainstem. Ventilation rate can also increase due to receptors in muscles and joints, but here there's like a lot of overlap with the chemoreceptors. And then kind of continuing counterclockwise, there are some other things that are going to try to, they also tend to decrease the amount of ventilation rate. And that's like irritants in the lung or stretch receptors in the lung. So, like when we were breathing together in class, when there comes a point when you almost feel your lungs all stretch out when everything's fully inflated. When I used to live in Colorado at high elevation, I found it very difficult to be able to kind of fill up my lungs to the point where they stretched, just because because the air was less thick there. But basically, those stretch receptors, the diaphragm can drop more. The intercostals can contract more, but doing so would end up damaging the lungs. Basically, you could pop those alveoli. So the stretch receptors prevent that kind of rough action on the on the lung tissue. The peripheral receptors. This is just a repeat of what I said before with the carotid body as well as the aortic bodies, but this includes basically where the sensory nerves that are sending the information up. Almost all the time we're talking about the vagus nerves. That's certainly what we see coming from the aortic bodies, but the carotid body is also is kind of drawn from the glossopharyngeal as well. That's how that information is getting up to the brainstem. Okay, that's what I got for this. That ends the respiratory system lectures. The next one I'm going to load up will be talking about the beginning of the digestive system. As before, be sure to load up any questions that you have, and I'd be happy to hear any feedback so that I can make this better, either this semester or make it better in the future. Thanks.